So today we are going to discuss about forces. Forces, then basic laws. Basic law. First, what do you mean by scalar? Scalar. Anyone can unmute and tell me scalar. Scalar. Quick.
Only magnitude.
Very good, very good. Parameter with magnitude only. Parameter with magnitude only. Example. What are the examples we can give? Regularly expected examples. Speed.
Distance.
Very good. Speed, distance. These two are regularly expected examples. Right. Then temperature also. All the temperature, heat related problems are called as scalar problems. Scalar problems, right? We have the special name for the temperature problems, right? Scalar problems, right? Then vector. What do you mean by vector? What do you mean by vector? Parameter with
Magnitude as well as direction.
very good, super. Parameter with magnitude and direction. Example. See, your example should be related to your department subjects, right? You should not give the unwanted examples in the interview. Right? Very good. Examples, expected examples. What is the vector quantity for related to speed? Velocity. Very good. Velocity. Velocity. For distance, what is the vector? For distance?
Displacement.
Displacement. Very good. Displacement. Right. Then force, acceleration, moment, both the bending moment and twisting moment, right? These are all vector quantities. Then tensor. Tensor. Any idea? Tensor. Parameter with magnitude direction and plane of action. Plane of action. For example, in which plane it is acting? The planes are mathematically represented by their normals. X normal plane, Y normal plane, Z normal plane, like that. Okay, means plane perpendicular to X axis is called as X normal plane. The plane perpendicular to Y axis is called as Y normal plane, right? We have to give the magnitude, direction, as well as in which plane the force is acting, the stress is acting, right? That we have to give. If you give like that, then the parameter is called as tensor. Right? Example is See, example is very, very important. Example, stress is a tensor. Stress is a tensor. Right. What about strain? Right. Strain means generally by default, strain means engineering strain. Strain means engineering strain. It is understood case, right? Strain is not a tensor. Not a tensor. Okay. Right. So if it is a tensor, we can use the Mohr circle. We can use the Mohr circle. If it is not a tensor, we cannot use the Mohr circle for transformation purpose. For transformation purpose, right, inside the material. For a stress case, we are doing the transformation process inside the material. At the end of the transformation process, we are calculating the internally transformed maximum normal stress, which is called as principal stress. Similarly, we can calculate tau max, maximum shear stress, right, inside the material. So those principal stresses and tau max cannot be calculated if the parameter is not a tensor. For example, with the help of engineering strain, we cannot calculate epsilon 1, epsilon 2, epsilon 3, gamma max. We cannot calculate with the help of engineering strain. So that is why we are saying that engineering strain is not a tensor, right? Sir, but we need to calculate maximum principal strain, minimum principal strain, maximum shear strain, sir. Compulsorily we need. What to do? Right. We have to convert the engineering strain into tensorial strain. We have to convert the engineering strain into tensorial strain. Right. Once it is converted, small modification, very small modification. Once it is converted, we can go for transformation. That is, we can use Mohr circle. Okay. Right. See, tensorial strain. Tensorial strain is a tensor. Right. So we have to do a small correction on the engineering strain to get the tensorial strain. Right. What is a correction? See, I'm writing engineering strain is represented by epsilon x, epsilon y, gamma xy. It is a engineering strain. Okay. Engineering strain. How to convert it into tensorial strains? Very small modification. No correction in the normal strain epsilon x. No correction in the normal strain epsilon y. Only correction in the shear strain gamma xy by 2 by 2. Only small correction. So the correction is only in the shear strain, not in the normal strain. It is called as tensorial strain. Right. Correction or modification. Modification to get tensorial strain. Right. So these things will not be in the textbook, right? Sir, where we are using the engineering strain, where we are using the tensorial strain, sir? That we want to know. Right. Engineering strain is used in the Hooke's law. Engineering strain is used in the Hooke's law. Right. See here, I will write the 2D Hooke's law, two-dimensional Hooke's law. Right. For the 2D, there are three cases: plane stress, plane strain, axisymmetric. Plane stress, plane strain, axisymmetric. I will write for plane stress. See, we are going to write the Hooke's law. Right. What is Hooke's law? Stress strain relationship equation. Stress and strain relationship equation is called as Hooke's law. Right. Sigma x, sigma y, tau xy. Sigma x is normal strain, sigma y is normal strain, tau xy is normal stress sigma x, normal stress sigma y, shear stress tau xy. Stresses, all are stresses. This is equal to E, Young's modulus, divided by 1 plus mu. Mu is Poisson ratio into 1 minus mu. Okay, into 1 mu 0, mu 1 0, 0 0 1 minus mu by 2. Right. Right. See, combinedly, this is a stress strain relationship matrix. Stress strain relationship matrix. Right. Then strain. Same color. Epsilon x, epsilon y, gamma xy. It is a engineering strain. Engineering strain. Okay, right. It is a Hooke's law, 2D Hooke's law, right? From here to here, right? See, actually, it will become a single number. It will become a single number. E by 1 plus mu into 1 minus mu will become a single number. If you multiply this number inside the matrix, you will get 3 cross 3. 3 cross 3, right? This 3 cross 3 is matrix. Yeah? This matrix is stress strain relationship matrix. Or another name is there, or constitutive matrix. Or constitutive matrix, right? This equation also called as constitutive equation, right? Okay, right. So this is the application of engineering strain. Sir, where we are using the tensorial strain, sir? In the Mohr circle. In the Mohr circle. Right. So Mohr circle is nothing but 2D transformation. 2D transformation. 2-dimension transformation. What we are doing, right? Mohr circle. Right. This is a Mohr circle like that, right? It is a 2D Mohr circle, right? For 3D also Mohr circle is there. For the 3D, 3 circles will be there. For the 3D, 3 circles will be there. For example, like this, right? That is 3D cases, right? But whatever we are doing in our UG, right? That is for 2D, right? So 2D transformation. It is nothing but Mohr circle equation. Epsilon x dash epsilon y dash gamma xy by 2 dash. Right. So it is our strain components after transformation. After transformation. Right. Then c square s square 2sc s square c square minus 2sc minus sc plus sc c square minus s square. Right. This is the transformation matrix. 2D transformation matrix. Right. 2D transformation matrix. C means cos theta. S means sin theta. Right. Then it is our epsilon x, epsilon y, gamma xy by 2. So before transformation, strain components before transformation. This is before transformation. This is after transformation. Right. In order to undergo the transformation process, the strain should be tensorial strain. It is a tensorial strain. Tensorial strain. Okay. Right. So it is our strain tensor before transformation. Right. This is strain tensor after transformation. Right. The whole equation is called as Mohr circle equation. Mohr circle equation. Okay. Right. So I will write the tensor format. I will write the tensor format. Just whatever we are discussing, right? It is a preliminary information only. We will study the tensor details completely in the strength of materials, right? Not in the engineering mechanics, right? So whatever we are giving, right? It is a preliminary information, just information only, right? Because when we are teaching the strength of material, you should not feel that it is a new one, right? You should feel that it is a familiar one to you, right? Stress. First, I am writing stress tensor. For 3D, we are writing sigma x, sigma xy, sigma xz, sigma xy, sigma yy, sigma yz, sigma xz, xz equal to zx, right? Sigma yz, sigma zz. It is a stress tensor. Stress tensor. Okay, right. Then strain tensor. Strain tensor means it is a tensorial strain, not engineering strain. Right. Epsilon xx, epsilon sorry, gamma, we will write gamma xy by 2 gamma xz by 2, then gamma xy by 2 epsilon yy gamma yz by 2 gamma xz by 2 gamma yz by 2 epsilon zz. Okay. See, it is a symmetric, right? Both stress tensor and strain tensor, both are symmetric. It is a strain tensor. For the 2D, this is whatever we have written, right? This is for 3D. For the 2D, very simple, sigma xx, sigma xy, that is tau xy. Sigma xy can be written as tau xy, sigma yy. Right. So it is our tau xz. Right. Then regarding the 2D strain, epsilon x gamma xy by 2 gamma xy by 2 epsilon y. It's a 2D strain tensor, right? So far we discussed about tensor information, right? Tensor information. Right? You should be aware of this, right? Repeating. Stress is a tensor. Strain is not a tensor. Strain means by default it is understood as a engineering strain. Right? Strain is not a tensor. See, in order to undergo transformation process, it means Mohr circle process, we have to convert the engineering strain into tensorial strain. Then only we can use the Mohr circle process, right, for strain transformation. Right. Where we are using the engineering strain in the Hooke's law. Right. Where we are using the tensorial strain in the Mohr circle. Okay. Right. This is Hooke's law. Actually, in the one dimension only, we are calling it as a Hooke's law. In case of 2D, we are calling it as a constitutive equation. Just for understanding purpose, we are writing it is a Hooke's law. 2D Hooke's law. Right. Then it is a Mohr circle. Mohr circle. Transformation means Mohr circle usage, right? In the Mohr circle, we have to use tensorial strain. So how to do the correction? Very small correction. Only in the shear strain. We are doing the correction. What type of correction? Divided by 2, that's all. Divided by 2. Very simple correction, right? Normal strains are normal strains. This is normal strain. No change. Only shear strain is converted, right? So this is about tensor details. Next, we are going to start with the force, right? Force, already you know, force is a vector. Right? In order to represent a vector, how many informations are required? Tell me. how many informations are required in order to represent two informations? One is magnitude, other one is direction, right? This is the general information. General information. See, this is the force. Force, applied force, right? Okay. The length of the arrow mark is nothing but magnitude. The length of the arrow mark is nothing but magnitude. Length of the arrow mark is nothing but magnitude. Okay, right. Then this point, right? It is called as point of application. Point of application. Point of application. Right. Right. Then another very important information is orientation. Orientation. Right. Right. So orientation is represented by theta. Theta. It is orientation. Orientation. Right. Then direction. Direction is nothing but tension or compression. Right. Tension or compression. The representation of tension compression is nothing but direction. In our case, in our diagram, this is compression or tension. Tell me.
Compression.
Compression. Very good. Very good. That kind of information is called as direction. Right. It may be tensile or compressive. Right. Then line of action. Line of action, very important information. Line of action. Okay. What is line of action? Line passing through that force is called as line of action. Right. Imaginary line passing through the force is called as line of action. Okay. Line of action. Right. See, initially we told that magnitude and direction both are enough. Right. Now tell me, without orientation, without theta, can you do the resolution, resultant, anything?
No.
No, no chance, right? So for comfortable calculations, we need all of these five informations for comfortable calculations: magnitude, direction, orientation, line of action, point of application. All are important for our comfortability. Okay.